We are using AI to dream up an incredible game concept and then bring it to life using Unreal Engine 5. We started off by using GPT-4 to brainstorm a unique game concept, then sketched out compelling characters, and even created a set of necessary documents, including a detailed level design document that is going to help us build the first chapter for our game. And now the real fun begins. We are going straight inside Unreal Engine to start setting up the character for our game using C++ code for the basic movement and camera controls, and then adding additional features like foot IK and eye blinking. Please watch this video till the end, and if you love what you see, don't forget to like, share and subscribe to my channel. So let's get started. Now that we have our initial concept ready, let's create a new C++ project because most of our gameplay functionalities are going to be in C++ since that's how I prefer doing it. Once the editor started, I will navigate to the Quixel Bridge interface and log into my account. Here, you have the option to choose from predefined metahuman assets or create your own one. For our demonstration, I will choose one of the metahumans and click on the Start MHC button right here in the bridge. Now that the metahuman creator is launched, let's begin our character creation process. The creator offers an impressive range of options, allowing you to blend between multiple faces and sculpting specific facial features. Although I am referring to the concept art generated by DALL-E 3, it is beyond the scope of this tutorial to create an exact replica of the concept. So for the sake of the demonstration, I will keep the metahuman design bare minimalistic and simple because our focus is rather on designing a compelling gameplay, not on perfecting character art. You can also create a completely custom metahuman face with a custom 3D head model and the metahuman animator plugin. I have made a separate video on that. If you're interested, the link is given in the description. Check that out as well. Alright, our metahuman is now created, so let's download it and add it to our project. Now let's take a look into the folder structure. So inside the metahuman folder, I see the folder called Elara, which is the name of the metahuman I just added to the project. In here I can see a blueprint. So I'm going to open it up. I'm getting a lot of errors regarding missing plugins. These are basically the dependency plugins for the metahuman. So I will press the enable missing buttons here and then restart the editor for the changes to take place. Okay, so now that my editor is restarted, let's open up the blueprint again. So I can see my metahuman in the viewport, and you can notice this hair glitch when you are at distance from the character, and that is because the hair is a groom asset which only works for the first two LODs. So I will quickly fix it by visiting the LOD sync component and setting the forced LOD to 0. This will ensure that the metahuman is always at the first LOD. Now we need to set up the metahuman as the main character that we can control in the game. But this is not a character blueprint, this is an actor blueprint. So we need to create a character blueprint. I'm going to develop most of the functionalities whenever possible in C++. Let's create a new plugin now. This plugin is going to have functionality specific to character movement, camera control, etc. So I will name this plugin as Extreme Locomotion System. I like to use plugins instead of adding C++ classes directly to the project source because it makes it easier to move the plugin between different projects and keeps the code structure clean and organized. Alright, so now let me ask GPT to create the code for the third person character class in C++. Our plugin is created and in here we are going to create our character class. So let's do that. So here we are going to copy the code that was generated by GPT. We are going to use the Unreal's latest enhanced input system, so we will not be needing this input binding. Let's go to the default character class. Here you can see the code for the enhanced input system, which uses the default mapping context asset that we need to refer from the content browser. We will do that later, but first let's just copy this code and add it to our class. So now we need to implement this hierarchy structure that you see in your metahuman actor so that we can replicate the functionalities of a metahuman. So I will create a snapshot of this and share it with GPT-4. GPT-4 is very much capable of reading a snapshot and understanding what the content is. Okay, so it is giving me the necessary code that I need to add in my character class. After a lot of modifications, this is how my code structure looks currently, where the components, torso, legs, feet, and face are skeletal mesh components, and rest of them like hair, eyelashes, eyebrows, etc. They all are going to be groom asset. On construction, I also have set up the parent mesh component as the leader of each of the skeletal meshes. That is because the animations are smoothly transferable from the master pose to the child pose whenever you set it up like this. So it is always recommended that when you have a hierarchy of multiple skeleton meshes, although they are sharing the same skeleton, but you should also set them up as master child pose reference. Now let's create a blueprint for our third person character. So first I will add the body mesh. Actually, let me make this into a base character blueprint and derive our player character from this. Now let's assign the rest of the body parts. So now we are going to set up basic movements for our character. In our mannequins folder, we are going to open up this RTG mannequin, and here we are going to set the target IK rig asset to our IK metahuman. I will quickly check if the animations are working correctly, and once I'm satisfied, I can just select the animations I want and click on the button export selected animations. Then I will choose the specific folder where I want to save the exported animation. So once I have the animations, I need to create an animation blueprint. So let's do that now. We are going to start with a new state machine. I will name it as locomotion. I will just add a single animation for now, which is the idle animation. Now I will create a C++ class derived from the anim instance, and I will name this class as extreme anim instance. So our anim blueprint is going to be derived from this particular class. In this class, I have introduced a couple of variables, speed and direction, and I am calculating their values in real time in the native update animation function. So the native update animation is an event that gets triggered at every frame. So depending on the character velocity and the direction it is facing, our variables are getting updated in real time, so we can use their values to drive the animations in our anim blueprint. I will now reparent the anim blueprint to use my anim instance class. So now I can add the walk animation. Its state is going to get determined by the value of the speed variable. We also need to ensure that loop animation is set to true for the animations which are supposed to loop until the condition to stop the animation is triggered. So next we need to set up the input system. If you remember the default mapping context variable that we have added in our character class, we can set its value to the mapping asset that comes with the third person character. Take a look into it and understand how it is set up first. So you can see the mappings currently we have is for movement, looking around and jumping. So each element in this mapping array is actually an input action asset where you can define the kind of movement you want to have for this particular mapping. For example, for move you have vector 2D because you want to move in forward as well as in right direction. For jump you only have it as boolean value because it can be either jumping or not jumping. The action look is going to be another vector 2D because it is going to determine whether you are looking along the x or the y axis. So before we add our input system in the blueprint, let's first create the camera component for our third person character. So here we added the spring arm component and the camera component that is going to be attached to the spring arm. And here also in the constructor, we need to define them like this. For our input, we have created a couple of functions, enhanced move and enhanced look, that we are going to call from the blueprint. So the enhanced move function is going to be responsible for moving forward and right direction, while the enhanced look function is going to be responsible for looking around in X and Y axis with mouse movement. Now to implement each of these events in our blueprint, we need to call the event corresponding to the action name. For example, if you want to call the event move, then the movement action is going to get triggered here. And here I need to call my function enhanced move, and we will pass the action value as vector 2D in the input parameter. Similarly, I will implement look along the X and Y axis. Now to test our player character, let's make a new game mode. And then in the default pawn class, I'm going to add our main character. Now in our class defaults, we also need to add the reference for our default mapping context parameter that we had defined in the C++. In the begin play, I'm going to initialize walk speed for the character because initially I want our character to just walk and then we will implement the run feature. Alright, the walking is working perfectly, but I'm not able to move the mouse in the Y direction. I think there must be some issue with the look function. Okay, so here the value type was bool actually, which is not correct. The value type is supposed to be vector 2D, so I just changed that. Also, the camera distance is a little too far. I will update that as well. Yeah, now it is perfect and I am also able to move the mouse in both the directions. So next I asked GPT to enhance our look function for smoother camera movement. So here I have defined mean and max pitch angle because I want to restrict the y-axis movement of the mouse. And I will add two more variables for controlling the yaw speed as well as the pitch speed. So I have made adjustments in my enhanced look function to ensure smoother camera movement via interpolation as well as restricting the camera pitch angle between the min and max so that camera does not go too high or too low below the character. Yeah, so as you can see, the camera movement looks much better and smoother right now. Now we are going to set up a blend space for our character. The blend space basically controls animation blending between multiple states depending on some parameter values. So blend space can be either in one direction or in two direction. So for now I will have the blend space only in the horizontal direction and I will be blending the animation based on speed. So let me add three animations over here: the idle, the walk and the run. Depending on the corresponding speed value, it will switch its animation state from walking to running. You don't necessarily need a blend space, but blend space actually helps you in creating a compact animation blueprint. Now in our animation blueprint, inside the locomotion state machine, I will add our blend space and I will control it based on the speed variable. Now I'm going to add another input action for running. Okay, so it is already of the type boolean, so I won't be modifying anything over here. So let's go back to our action mappings. And here I'm going to create a new mapping. I will assign the run action over here. And in key binding I will add left shift. So what I want is for the character to run when I'm holding the left shift. So now in our blueprint we need to call the function and we also need to define what's going to happen when I'm pressing run in our C++ character class. So let's do that now. Here I'm adding a variable is running. And also let's create a blueprint callable function called toggle run. This will set our is running variable to either true or false. And based on the current value of the variable, I will simply change the walk speed of our character, and our blend space is going to take care of the rest. In the begin play, we can set the walk speed of our character, ensuring that by default the character is going to walk. Now here I'm going to add our run input action, where I can simply call the toggle run function. Okay, so slight modifications required here. What I meant to do was running when shift is being pressed. So actually I need to pass the state of action from this event instead of toggling the boolean variable directly in C++. So I will just make a modification in our function to add a boolean parameter. So this function is going to be get called twice when it is triggered and also when it is completed. I also want to increase the camera distance from the character when the character is running. So for that, I am simply interpolating between two different arm lengths for our spring arm component in the tick event, depending on if the character is walking or running. Now let's test our running and the camera distance as well. Perfect. Now when I'm pressing shift, my character is running and the camera distance is also increasing. And when I'm releasing shift, she is going back to walking, and also the camera distance is lerping towards the original value. So next I'm going to implement foot IK for our character. As you can see, that feature is already present in our mannequin, so I have to simply understand how it is set up in the mannequin and just have to replicate it in the metahuman character. We need to understand control rig to set up the foot IK for our character. If you are not familiar with control rigs, I might do a video on it later, but for now let's open the basic foot IK control rig asset for the mannequin. So I created a similar control rig for the metahuman as well. We just need to replicate the functionalities from the mannequin to the metahuman. Let's understand the foot IK setup first. So if should do IK trace is true and this variable is being passed from the anim blueprint, if this is true, then this foot IK trace function is being called. So let's see what's happening inside the function. So it is doing a sphere trace. So the start location is going to be value slightly above your IK foot bone, and the end location is going to be a value slightly below your IK foot bone. So based on the value from the foot IK trace, it is setting the Z offset both for the left and the right feet. It is doing a little interpolation over here, and based on the minimum value of the left and right Z offset, it is calculating the Z offset for the pelvis to determine exactly how much the pelvis should be bent to adjust for the foot extension. Over here, it is modifying the respective IK foot bones and the pelvis bone. And finally, it is doing the full body IK. Now we need to replicate this in our metahuman. So let's just do that. Okay, so the metahuman actually does not have the IK foot bones. That's why the feet are not coming right. And the only solution out here is to add virtual bones, and not from here, but rather from the skeletal editor. So here I added a virtual bone for the foot root and then two virtual bone for the left foot and the right foot. So let me also name this appropriately. Here I will also create a couple of variables that will work as reference to our left and right IK food bones respectively. Okay, so now in our anim blueprint, we need to set up the control rig. So there is a control rig node for that. In here, we need to assign the control rig we are going to be using for this. In the control rig class, I added my basic IK control rig. So here we need to make the should to IK trace variable public so that it is accessible via the control rig node here. Now we can make this into a variable within the anim blueprint itself. Perfect. So its default value is going to be true. Now let's test it out. Look at that, the result is perfect. Yeah, I love it. I love how accurate the food IK is. Let me go to the higher ground in order to test further. Yeah, perfect, right? This is really a great result. And the best part is we didn't even have to put much effort in order to achieve the desired outcome. So now we need to implement eye blinking for our character because currently the character is constantly staring and it doesn't look very realistic. So let's take a look into the face anim blueprint. Here you can see already several of the facial animations have been set up with this modify curve node. By changing the respective floating values here, you can actually modify some of the facial animations. So we are going to set up something very similar for the eye blink as well. I will add a modify curve node here. For our curve pin, we are going to look for control expression eye blink L and control expression eye blink R. And now with a little help from GPT, I created another class called extreme face anim instance, which is going to be the parent class for our face anim blueprint and is going to contain the functionality for the eye blink. Alright, so I am adding a few parameters which are going to determine the blink interval and the blink duration respectively. So here this iBlink alpha variable is going to control our blink alpha. Additionally, we can control this blink interval and blink duration parameters. Yeah, working perfectly as you can see. Okay, so next I'm going to implement the falling mechanism for our metahuman. I'm not assigning additional input for the jump for now. I only want to do a fall when it is dropping from a higher ground. So for that I basically need two animations. One is the fall animation and the second is the land animation. And both of them I retargeted from the mannequin. So here I'm going to make this locomotion state machine into a cast pose so that it can be accessible multiple times. You can see in the mannequin anim blueprint how they have set up the jump, fall, land anim state. So I did something very similar in our metahuman anim blueprint as well. The land animation is actually an additive animation that needed to be applied on top of the locomotion state machines. So let's test this out. Yeah, see the jump as well as the land is working perfectly. Alright. You can also test it out with the run animation as well. Yeah, so far it's perfect. Alright, that concludes today's episode. The plugin Extreme Locomotion System which we have built for today's video is also available on my Patreon page, so consider supporting my work by becoming a member. The link is given in the description. Your support helps me create more such amazing contents. In the next episode, we will dive into designing our first sequence with the help of generative AI and explore building NPC metahumans for dynamic interactions. So don't forget to hit that like button, share this video if you learned something cool, and subscribe for more awesome contents. See you soon.